Hey everyone, welcome to the lecture for 12.2. So we're going to talk about scatter plots and correlation. So first we want to start by understanding correlation visually. So the way that we do that is with scatter plots. So scatter plots take two sets of data. So think about maybe having two different populations, two different random variables, and you have two samples one from population X and one from population Y. And so what you do is you kind of match them up and create these ordered pairs, and then you plot them. And so we can see in these first three graphs up here, we have three different pairs of sample data, and we've plotted them on an X and Y axis. So the first example, it looks like there's some sort of trend, right? Like maybe there's some sort of link. And by this, I mean, maybe there's some sort of correlation between the two variables. In the middle picture, I would feel strongly that there definitely is correlation, right? So you could almost imagine like a trend line kind of cutting through the data and getting pretty close to a lot of the points that we see plotted here. In the third example, it looks just absolutely crazy and random, and this would actually be an example of no correlation. So later on in today's lecture, we're going to see how can we tell numerically what kind of correlation is going on. But first, let's just talk about how to plot these data values. So making a scatter plot by hand is really as simple as just kind of syncing up your data in our table and then just plotting it as a pair. So we can see here that we've got X equals 8 and Y equals 7. So I'm going to plot that point considering that this is the x-axis and this is the y-axis. I'm going to plot the point 8, 7. So that's over 8 on my x-axis. And then I'm going to go up to 7 on my y-axis. So that's my first point here. Next, I'm going to look at the next pair of data, 4, 4. So I'm going to plot 4 on my x and then go up to 4 on my y, giving me that point there. The next pair of data I have are 7 and 6. So I want to go over to 7 on my x and then go up to 8 on y. Oh, sorry, 6. Let's go back down. Here we are, 7, 6. So just with these three data points, it almost feels like it's almost a straight line, but it's actually not quite. Let's see what these other two give us. So 6, 3, that's 6 up 3. And then the last one is 3, 8. So that is how you would compute a scatter plot by hand. So if the graph kind of suggests that the data is moving up and the right together, as possibly this one is, then that's going to represent a positive correlation. If the graph is going down and to the right, then that's going to represent a negative correlation. So let's revisit our first two examples at the top of the page. Here we can see that we definitely kind of have a trend going up and to the right. Whereas over here, I've got a trend going down and to the right. So this is going to represent a positive correlation. And this one's going to represent a negative correlation. This one was no correlation, as we said earlier. But there's something more. There's more information here. Notice that the first graph where I said that there's positive correlation, the plotted points, they aren't as tightly fit to this line that I've just drawn. Whereas if I look at our example with negative correlation in the middle, the line tends to be less far away from the plotted points. And so now we can talk about the idea of strong, weak, and moderate correlation. So I would say that in the middle graph, the data is more strongly correlated, right? It's kind of like a tighter pack. Whereas on the first example, on the left side for positive correlation, I still have good correlation, but maybe not as strong as the middle example. So how can we actually quantify what is strong, what is weak, what is moderate? So there is a way, which we'll discuss in a second, to measure numerically correlation. When we get a measure of our correlation, it's going to be a number between -1 and +1. So here we've got a chart that shows kind of like the common scales for what different disciplines consider to be strong, moderate, or weak correlation. So when we have a positive output for our correlation, that's going to be a positive correlation. And when we have a negative output for a correlation, that's going to be a negative correlation. So I can have a strong positive correlation, and I can also have a strong negative correlation. So let's look at how all this stuff is computed. So we are going to consider these graphs, and let's see if we can figure out who's strong and who's weak, and then we'll jump to, well, what number are we supposed to get anyway? So in this first example here, this is what I'm going to say is a perfect correlation, because I can draw a line straight through all of these points, right? There's nothing that's deviating away from this line. So that represents perfect correlation. And because it's going up and to the right, it's positive. In the example directly below it, this is also a perfect correlation, but it's going down and to the right, and so it's negative. So they have the same strength of correlation. One is positive, one is negative. Here we have a decent correlation. If we're kind of to draw just a line through it, it's definitely trending with that line, and we can see it's going up to the right, so it's positive. You could say that this is a strong correlation. Possibly you might argue that it's moderate. I'm saving my moderate for my next examples then. And then similarly, we've got a good strong correlation here, but it's going down and to the right, so this is going to be negative, but still strong. And then in these other examples, definitely there's trending up and to the right, but you can see that our points, our plotted points, our XY pairs, they're further away from this trend line, right? So it's more spaced out. There's more variation away from this line. So while it is positive, you might say that it's moderate. You might say it's weak. It's kind of open for interpretation. And similarly, the example right below it, perhaps not a great line. Let's see. This is going to be negative, and this would be moderate or weak. And then in this last example on the right, what's interesting here is that it almost looks like my trend line goes just straight across. So when you have a trend line that goes straight across like this, then this is going to be no correlation. One of the things that we're going to use correlation for is prediction, right? So if we kind of looked at this first example where we have a perfect positive, let's say I had a data value over here, like I knew that X was going to be over here. This trend tells me that I can expect my Y value to be at this height, right? So it's kind of like a predictor for what's going to happen next. And the stronger your correlation, the better it is at predicting. So let's do an example where we're actually now going to compute the correlation coefficient. So the correlation coefficient is kind of a wild equation. And I'm sure you've already guessed that we have an Excel sheet for this. So let's pull up that Excel sheet and we'll see how it's done. All right, so once we have our Excel sheet open, we'll notice at the bottom right, after our Z and T tests for mean and proportion, we have a tab for correlation. And all we want to do is we just want to take these values and we want to copy them into our Excel sheet. So once our data is copied into our Excel sheet, then what is produced is a scatter plot. So if I was so inclined, I could copy it into my OneNote. And I can also see here at the bottom that I have something called the correlation coefficient. So it gives me a value for R. R is the symbol for the correlation coefficient. And here I have that R equals 0.3136. So what does a correlation coefficient of 0.3136 really mean? I mean, we can definitely see that there's a bit of a trend line, right? If I were kind of just to like do something like that. But how closely correlated are these? Is it weak? Is it strong? Is it moderate? We know it's positive, right? It's going up and to the right. And guess what? R is positive. So by sheer fact that R is greater than 0, we already know it's a positive correlation. But that just matches what our eyes are telling us when we look at this scatter plot. So let's see how we fare against this table. So if we use the psychology scale, we're about +3. So this is a little bit above 3. So maybe we could say it's a weak to moderate positive correlation. All right, so that one was kind of straightforward, right? We were given our data X and we were given our data Y. But could we have explained X as affecting Y? And is there more to this story? Well, what was X? X was sunlight in California measured in kilojoules per square mile. And Y was per capita consumption of sour cream by the half pint. So I don't know, does one affect the other? I'm leaning towards the fact that this is just mere coincidence. And this brings us to a really important statement, is that correlation is not causation. We cannot look at two variables being correlated, even if we had like R equaled 0.99999 here. Just because they're strongly correlated, or just because they're correlated at all, it does not mean that we have a causation between the two. That doesn't mean that one causes the other. Right? So I'm just going to continue to live my life with the belief that sunlight in California does not directly impact the per capita consumption of sour cream by the half pint. But there are cases where correlation is implying causation. So let's consider this. Consider that we were collecting data for the following pair of variables. We're going to check depth versus visibility. So if you've ever been diving before, the further down in the water you go, the less sunlight penetrates through the water and your visibility gets less and less. Now, there are, of course, other factors for visibility, like the amount of disturbance in the water. But if we were to look at this very simply, very topically, we actually could justifiably say that the explanatory variable, kind of like the independent variable, the one that is going to determine what the other one is, the explanatory variable is going to be depth, right? Because the further down you go, the harder it is to see. And then the variable that responds to depth, the thing that's changing based on depth, the response variable, that's going to be visibility. And so let's think, would we expect a positive correlation, a negative correlation, or no correlation? Well, you might think, I guess it depends on how you measure depth, right? So how about this? As depth increases, right? You're diving deeper. Your visibility decreases, right? It gets darker. So as depth is going up, visibility is going down. So let's think about this in the context of plotting on an XY grid. So much like we've seen in algebra, you want to plot your explanatory or independent variable along the horizontal axis. And then you want to plot your response or dependent variable along the y-axis. Because y depends on x, or so we're assuming here at this point. So think about this, as I move along and increase my depth, as I'm doing that, the visibility, if I'm really near the surface, my visibility should be pretty high. And then as my depth increases, my visibility is going to decrease, right? So we're going to have a decrease in visibility. So what's going to happen is that we're going to have a strong negative correlation. And in this case here, you could argue that it's not merely correlation, it's actually causation. But just remember that whenever you're doing correlation, you can't just jump to the conclusion that it's causational. Like you have to just keep it at correlation until given better evidence.